We have part 4 of our 4-part series addressing the application of alkalinity concepts. In this video, we'll do a detailed analysis of the relative error associated with several common simplifying assumptions used in interpretation of alkalinity titration results. In part 2 of this series, for interpretation of alkalinity titration results, we developed a corrected equation relating the measured alkalinity to the abundances of carbonate and water species. Here we have the molar concentration of alkalinity, and we equate that to the initial bicarbonate, twice the initial carbonate, the initial hydroxide, less the initial hydronium ion concentration, plus the final hydronium ion concentration. The alkalinity, of course, has to be a molar concentration, and so therefore we take our result in milligrams per liter as calcium carbonate, and we modify it by 1 mole of alkalinity per 50,000 milligrams as calcium carbonate. Then, as long as the initial pH of a water sample is above about 6.3, the error in neglecting the initial hydronium ion concentration is small, as the initial hydronium is less than 1/100th of the final hydronium ion concentration of the titration. Then, as we did in part 3 of this series, we employ a very close approximation to be the true value. In part 3, we employed the carbonate-bicarbonate equilibrium to obtain a relation between alkalinity and bicarbonate, initial hydroxide concentration, and final pH of the titration. A little algebra resulted in a relation used to find the bicarbonate concentration. Then we computed the total inorganic carbon from the computed bicarbonate and alpha 1. So let's use the function writing capability of a MathCAD worksheet to create a series of functions, measured alkalinity, to explore the errors associated with the various levels of simplifying assumptions. We'll plot that over various ranges of measured alkalinity. So we examined 3 levels of simplifying assumptions rather than 2. We'll neglect hydroxide, carbonate, and the final hydrogen ion concentration. We'll neglect just hydroxide and the final hydrogen ion concentration. And we'll neglect only the final hydrogen ion concentration. We write our functions using alkalinity as milligrams per liter as calcium carbonate, necessitating that we put that conversion factor right into the functions where it belongs in all cases. Since alkalinity would be milligrams per liter as calcium carbonate, all of the remaining concentrations would be molar concentrations. We write additional functions that allow us to compute the total carbonate from the bicarbonate and the alpha 1 value. We set up relative error computations, much like we had before, where now we have the relative error of approximation 1 versus the true value, the relative error of approximation 2 versus the true value, and the relative error of approximation 3 versus the true value. And we'll take those 3 relative error functions and we'll plot them, after we calculate them, of course, versus measured alkalinity over the range of 3 to 300 milligrams per liter as calcium carbonate. So we have a plot of our analysis results at pH 7.5. One thing that we can note is that below a measured alkalinity of about 50 milligrams per liter as calcium carbonate, there is no difference, essentially, among the 3 approximations. As alkalinity ranges above about 100 milligrams per liter as calcium carbonate, we start to see some error associated with the neglect of the carbonate ion. The significant aspect of these results is that the neglect of the final hydrogen ion concentration is very, very significant, and that when we approach single-digit measured alkalinity values, the error in the computed total carbonate concentration approaches and exceeds 100%. So we've been specific to pH 7.5, and since we've put together a computational model in our worksheet, it's very, very easy to insert differing values of pH and see how the system might behave at other pH values. So we did this at pH 6.5, and we see that the only significant error across the whole range of measured alkalinity values that we've considered is the neglect of the final hydrogen ion concentration, which again, as we approach single-digit alkalinity values, gives us relative errors in excess of 100%. At pH 8.5, same situation at low alkalinity values. And then, of course, at higher alkalinity values, we see that neglect of the carbonate ion concentration begins to result in very significant errors. So much of the published understanding of environmental water chemistry was developed well before the availability of convenient numerical modeling software, such as MathCAD15. And unfortunately, many of the methods used for interpretation of analyses, such as alkalinity, still depend on simplifying assumptions necessary to the pencil, paper, calculator solutions of many years ago. This series of video examples illustrates the use of a convenient approach that minimizes the necessity for employing simplifying assumptions in water chemistry calculations. And as a consequence of our analyses, we think maybe that alkalinity results should be adjusted, or interpretation protocols should be rewritten to account for the final pH of the alkalinity test.